Hey everyone, and welcome. Have you ever stopped to think about the secret life of the metal in your phone or in your car? Well, that's exactly what we're diving into today. The incredible hidden journey that starts with a simple rock and ends with the materials that build our entire world. It's a real hero story. So let's get right into it.
So, really, how does it all happen? How do we go from a pile of what looks like ordinary rocks into something as specific and useful as the copper wires powering your phone or the lightweight aluminum that lets an airplane fly? That's the epic journey we're going to follow.
You know, every hero's story starts somewhere, and for our metal, it begins in captivity. You see, with just a few exceptions, think gold or silver, most metals aren't just lying around out there for us to pick up. Nope, they're actually chemically trapped, locked inside these things we call minerals.
Okay, so this is a really important distinction here. While a mineral is pretty much any natural rock that has some metal in it, like China clay, which contains aluminum, an ore is special. An ore is a mineral where it's actually worth it, both economically and practically, to get the metal out. So yeah, China clay has aluminum, but bauxite is the real treasure we're after. That's the ore.
So, once we've found our ore, our hero faces its first big challenge, getting separated from all the worthless junk it's mixed with. This is all about separating the treasure from the trash. And this whole crucial first step, it's called concentration. And you know, every hero needs a villain. In our story, the villain is called Ganyu. And that's just a fancy, technical term for all the junk, the sand, the rock, all the other worthless impurities that are physically mixed in with our good stuff. The first goal is simple: get rid of the Ganyu. So how do we defeat the gang? Well, first we take the big chunks of ore and crush them into a fine powder. Then, one simple way is a hydraulic wash, where running water just carries away the lighter gang. But for certain types, like the sulfide ores that give us lead or zinc, we get even more clever. We use this amazing process called froth flotation. It's basically like a specialized bubble bath for minerals, where pine oil helps the valuable ore particles cling to air bubbles and float right to the surface, leaving all that gang to sink. Pretty cool, right?
Okay, so our concentrated ore has survived its first trials, but now it faces the absolute climax of its journey. To truly free the metal from its chemical prison, it has to endure a trial by fire.
And this trial is called smelting. It's this super intense process where we heat the ore in a furnace to just crazy high temperatures. And that heat, plus a little chemical helper called a reducing agent, which you can kind of think of as something that swoops in to steal oxygen away, that's what finally breaks the chemical bonds holding our metal hero captive.
But there's another secret ingredient in this fiery recipe: flux. Think of flux like a chemical cleaner. We add it in during smelting, and it latches onto any leftover gang. Together, they form this molten, glassy waste product called slag. And because the slag is lighter than the molten metal, it just floats on top, and we can easily skim it away.
And the result of all this? Our metal hero is finally free. But it's not perfect yet. It's a crude, impure version. For instance, when you smelt copper, you get these bubbles of sulfur dioxide gas escaping as it cools. That leaves this rough, bubbly surface on the metal, which is why they call it blister copper. It's the perfect name, right? Our hero is free, but it's clearly been through a battle.
You know, this all sounds incredibly precise, doesn't it? Smelting isn't just about making things super hot. It's about hitting the exact right temperature for a specific metal and a specific reducing agent. So that brings up a huge question. How on earth did scientists and metallurgists figure all this out?
The answer is just pure genius. They figured it out with this incredible tool called the Ellingham diagram, and it's essentially a secret map for chemists, a guide that unlocks the entire science behind smelting. Okay, so here's how you read this map. See all those lines? Each one is a different metal ore. And the lower down a line is, the more stubborn it is. It really doesn't want to give up its oxygen. Now, that orange line represents our reducing agent, carbon. The magic happens right where the carbon line dips below a metals line. That's the sweet spot. At any temperature past that crossing point, the carbon basically wants the oxygen more than the metal does. And bam, that's when you know the reaction will work. It's your green light to start smelting.
So, our hero has won its freedom. But it's still a little, rough around the edges, still full of impurities. It needs one final transformation to reach its full potential. And that brings us to the refining stage.
And why is this step so critical? Well, the difference is just night and day. Crude metal? It's often brittle. It's a terrible conductor of electricity.
But after refining, it becomes ductile, malleable, an excellent conductor. All those amazing properties that we love about metals, they really come out in this final purification step.
And we have some seriously clever methods for this. For example, there's electrolytic refining, which uses electricity to dissolve the crude metal and then replate it as a super pure version, leaving all the junk behind as this stuff called anode mud. Or how about zone refining? This is crucial for making silicone for computer chips. You use a heater that moves along a rod, and it literally pushes all the impurities to one end, which you then just chop off. It's absolutely brilliant stuff.
So after this whole epic journey, from being trapped in a rock, surviving trials by water and fire, and going through that final transformation, our metal hero is finally ready. It's ready to fulfill its destiny in our world.
And this is where it all comes home, right? That purified aluminum, that's what makes airplanes so lightweight. That pure copper, it's the wiring that's literally powering your screen right now. And that gold, yeah, it's beautiful in jewelry, but it's also inside our most advanced electronics as critical connectors. Their long journey ends as a part of ours.
Now, you might be thinking this is all modern science, but humans have been mastering metallurgy for a very, very long time. How long? Just consider this number for a second. 1600.
That, right there, is the age of the Iron Pillar of Delhi. Think about that. For over 1,600 years, this massive iron pillar has been standing out in the open, exposed to all the elements, and it has barely rusted. It is an absolute marvel, a totally stunning testament to the incredible skills of ancient Indian metallurgists.
So what's the secret? How is that even possible? Well, scientists figured out that it's protected by this incredibly thin, perfectly uniform layer of a special compound called mesawite. It's this natural corrosion-resistant film that formed over time and has just kept it pristine for centuries. It's amazing.
And it really makes you think, doesn't it? Just like those ancient innovators mastered iron and literally forged the Iron Age, all of the processes we've talked about today are the foundation of our modern world. So it leaves us with a pretty big question. What new materials with their own incredible heroes' journeys are we going to forge to define our future?